Most of the interesting and paradoxical seeming results in quantum mechanics involve more than one particle, but so far we've mostly covered the maths of just a single particle at a time. So in this video, we're going to go over the 3 rules of quantum mechanics again in the context of 2 particles or more. And eventually you'll learn all the mathematics you'll need to be able to pick up papers about, let's say, Bell's theorem, or no cloning, or no signaling, all of those kind of things. Now you might remember that the first rule of quantum mechanics that we met was called the Superposition Rule, and it said that all states are vectors. And we've seen some examples of that. So for example, with electrons and their spin, we can have the state of this electron being A times up plus B times down. And that kind of state is called a vector. We've also seen similar examples for light. So for example, this second particle, its state might be C times horizontal plus D times vertical. And so far this rule has made sense. But what about if I don't want to just talk about the state of this particle and that particle separately? I want to talk about them together. Well, actually, in this case, it's really straightforward. The joint state, so the state of particle 1 and particle 2 at the same time, is this. It's just taking the state of the first particle and putting it next to the state of the second particle. And this is also a vector. For states that represent multiple particles, when you have a state of multiple particles like this, the first bit of the state represents the first particle. The second bit of the state represents the second. Here I've color-coded it so that it's easier to see, but it's very important that the order stays the same. I should never accidentally put the second particle first, because the first bit here belongs to the first particle. So that is really the only thing that you have to keep in mind. Well, this example looks very neat when the 2 states are packaged up like this. But remember, state 1 is equal to this whole thing, and state 2 is equal to this whole thing. So what if I want to write this state in terms of its actual basis vectors, so in this case both up, down, and horizontal, vertical? Well, I can. All I have to do is expand the brackets. I mean, we could just join the 2 states together by keeping them in their brackets, but if you really want to expand it out, this is what it'll look like. So first we take this term, and we multiply it by that term. Now A and C are just numbers, so we can just pull those out to the front. So we'll put A times C, and the order of those 2 numbers obviously doesn't matter when you're multiplying them. It doesn't matter if it's A times C or C times A. They're both the same. But on the other hand, the next bit, the order does matter. So it's up and then horizontal. And so remember, that's because the first bit of this vector represents the first particle, the second bit of the vector represents the second particle. So we got to keep it in this order. Next, let's multiply out this term with that term. And then this term times that term, and this term times that term. And so this is the result. I know that that was kind of boring to watch and also quite painful, especially considering it would have been perfectly good to just leave the state like this. But I did want to show you once just how to expand these kind of brackets, because it's going to be very important when we start talking about entanglement. You see, for entangled states, like we talked about last time, it's not possible to just talk about the state of this particle separately to the state of this particle. And so you'll always have to write some sort of joint state. This, for example, is an entangled state, and that's because the state of this particle is going to depend on the state of this one. Here's what I mean. So if we just look at the first part, you can see that it says this is up when this one is down. On the other hand, it's down when the other one is up. And so the state of whether this is up or down depends on what this one is doing, and vice versa. The definition of entangled is that you can't write it like this. You can't just say the state of particle 1 is this and the state of particle 2 is this independently. Instead, you have to write it in some way like this, where there's something for particle 1, something for particle 2, plus something else for particle 1, something else for particle 2. But sometimes it's not that obvious when a state is entangled or when you can actually write it in a factorized form like this. So here's an example. What if I simply change the down here to up? Now this is no longer an entangled state. And to see that, you're going to have to factorize the state. So again, treat it very much how you would treat regular brackets and factorizing numbers. If we're trying to factorize, we're trying to find the common factor in these two terms. And clearly the 1 on square root 2 is a common factor, so I'll just pull that out. That's no big deal, that's just a number. But there is also this up that's common in both of them. So I'm going to put up here. And then we'll have some brackets for dealing with these two. To make sure that this is truly the same state as that, we can practice multiplying everything out again. So if we take this first term, we multiply it by this, we'll get up horizontal, which is this term. And then if we go up vertical, that's this term. So this is the same state as that. And now I'm going to do one last thing to make it a little bit neater. I'm going to take this 1 on square root 2 and put it into here. And the reason for that is because right now, this is not a normalized vector, right? Because there aren't factors here that make this whole vector equal to length 1. And each of the individual component vectors should be length 1. So I'll take this 1 on square root 2 from here. I'm going to put it in there. And just to make it even neater, remember that this vector is the same as the 45-degree vector. So why don't we just replace this? And that there shows that this original state was not entangled. It was possible to write it as a state for the first particle and another state for the second particle. The two states are basically independent of each other. When I first started doing calculations like this, I used to find them somewhat confusing because it is really easy to accidentally swap the two particle states around and that sort of thing. And it's kind of weird to think about the factorizing where you can like pull out just one of the particle states. It is all like quite difficult to get your head around. So I'd recommend just trying to write a few states and seeing how far you can factorize them. So you could put here whatever you want. You can put whatever numbers in here that make this normalized, and then you can just practice seeing how far you can factorize it and then deciding whether the state is entangled or not entangled. I know that doing a bunch of maths problems is not everyone's idea of a really great weekend, but I do think that it is worth getting kind of familiar with this stuff if you're interested in then going on and understanding various like paradoxes in quantum mechanics or just even very interesting results. For example, one of my favorite results in quantum information theory is called quantum teleportation. And it's really, really beautiful, but to be able to understand it, you need to be able to do this kind of maths fairly confidently. So I do recommend just trying to do these kind of problems. If you need a little bit more guidance and structure and maybe a little bit more motivation for learning all this stuff, then there is going to be a live version of this course. And the whole idea is that it's centered around learning to do problems. So every week there will be tutorials and homework problems, and we will go through problems like this, and you'll get to practice doing them for yourself. If you're interested, there's a link in the description. Alright, so let's go on to the second rule of quantum mechanics, which is called the Born rule, and it's for calculating probabilities. Here's how you do it. For a single particle, if I wanted to find the probability that it is going to be horizontal, then I look at that coefficient and I take the mod squared of it. If, on the other hand, I'm not interested in the probability of horizontal and vertical, but I'm interested in some other basis, let's say this one, then I have to rewrite the state into that basis first. So I have to rewrite my vector in this basis, and once I've done that, then I can look at the coefficients and take the mod squared of those coefficients to find the probabilities. So for example, for this basis, that might look like this. I rewrote the state in terms of this vector and this vector. I looked at those coefficients, and to find this probability, I mod square that coefficient. So the updated Born rule that we're going to learn now for multiple particles is very, very similar. All it comes down to is first writing the state in the correct basis and then looking at the coefficients. However, there is one extra wrinkle, and that is that sometimes you may measure both of these two particles at the same time, but sometimes you might just want to measure one or the other. And so for that, we have to have slightly different rules. Let's say that this is the state of our two particles. So it has a coefficient of square root 3 on 4 of up horizontal and a coefficient of 1 on square root 4 for down vertical. Now, it makes sense to talk about measuring one of these particles without the other, because while the state of these two objects is entangled, physically these are two separate things, and so they might have even ended up flying very, very far away from each other, and they really are separate. So, if you had this electron fly into your lab, you could do a Stern-Gerlach experiment on this electron, and that isn't a problem at all. On the other hand, if you had gotten this particle, you also could have just done a completely separate measurement of that particle. So let's talk about what would happen in those two cases. So if someone just got a Stern-Gerlach machine and measured whether this electron is up or down, what is going to be the probability that it goes up? It's what you would expect, actually. You look at the state and you look for the bit that has the up vector in it, and then you look at its coefficient, and you take the mod squared of it, which in this case would be 3/4. So the probability that this state gets measured as up is 3/4. And to find the probability that it's down, you look for the bit of the state that has down in it, and then you look at its coefficient and you square that. The one wrinkle here is that it is possible with these kinds of states to have more than one component that has up. And what do you do in that case? Well, you factorize. Factorize all the up terms together and then look at the coefficient. You do have to be a little bit careful with all of this factorizing business though, because you want to make sure that whenever you're looking at these coefficients and using them for these probability calculations, you have to make sure that both of these vectors are length 1. In this case, it's obvious, but imagine that I finished factorizing a vector and I got this result, where this is the only term that has an up in it and there are other terms here that involves down. So I would think, well, I just have to look at the coefficient for up and then take the mod square of it. So this should be 1/4. But that's not correct. And the reason is that this vector does not have length 1. So first I need to normalize it. This needs to have a 1 on square root 2 for both of these so that that vector has length 1. But if I put in a factor of 1 on square root 2 here, then I need to take it out over there. So I'm going to divide by 1 on square root 2, which is the same as multiplying by 1 on square root 2. And then if I want to find the probabilities, it is the square root of 2/4 squared, which is 1/2. Rather than 1/4 like we predicted before. I know that that makes it seem really complicated, but genuinely it's not that complicated, and most of the time you won't have to worry about making sure all of the vectors are length 1 because they'll very obviously be length 1. But I do want you to be a little bit careful about this. But let's go back to the entangled state that we were talking about earlier. So we had this state, and we found that if we were just going to measure the electron, the probability it would be up would be 3/4. And the same sort of maths would apply to this light. The probability that it will end up being vertical is also 3/4. But now let's start talking about joint measurements. Let's say I want to find out what is the probability of getting both up and horizontal. Just intuitively, what do you think this probability should be? Because if you look at this state, there is no part that's both up and horizontal at the same time. There's up and vertical, and there's down and horizontal, but no up and horizontal. And yet, we just said that the probability of getting up is 3/4, and the probability of getting horizontal is 1/4. So shouldn't we just multiply those two together to get this probability? Well, no, that's not how joint probability distributions work, right? Because these two particles are related to each other, the outcomes of these kind of joint measurements are also going to be related to each other. And in this case, this probability should actually be 0. What do we actually mean by this? What we mean is if Alice was doing her measurement on this electron and Bob was doing his measurement on this light, and afterwards they come together and talk about their results, then they're going to find that there was never any chance that Alice measured up and Bob measured vertical. On the other hand, what's this probability? Well, for this, we just have to find a part of the state that matches up with these outcomes. So it's this coefficient mod squared. What this means is that when Alice and Bob come back together and they talk about their results, 3/4 of the time it will happen that Bob has gotten up and Alice has gotten vertical. So the probability rule for joint measurements is very, very similar to what we were talking about for single measurements and even for single particles. All you do is, if you want to find the probability of something like this, then you write the state in the correct basis. So in this case, you need to have the first particle in the up-down basis and the second particle in the horizontal-vertical basis. So we've done that. And then you look for the coefficient that represents that joint outcome, and you take the modulus squared of it. So that is the measurement rule for joint particles for most cases. But there is actually one last case, which is quite tricky and conceptually a little bit difficult as well, and also mathematically a little bit difficult. But I'd like to tell you about it so that you know these exist, because I think they're very important. So there are other types of measurements that you can do on these individual particles that aren't individual measurements. So remember, the measurement we were just talking about was doing a Stern-Gerlach machine measurement on this, and then doing a filter, a polarization filter measurement on this. So you can basically talk about those measurements separately. But there are some measurements that you can only do if you have both particles and you put both of them into the same measurement machine. But what are these measurements, and why would you ever want to do them? Well, actually, one interesting case is if you wanted to figure out if your particles are still entangled. So let's say that these two particles are originally entangled in a particular state, and I just want to check, are they still in that state or not? Remember I said earlier that it's very, very hard to keep a quantum superposition, and it's even more hard to keep this entangled state pure, because there are going to be so many other particles bombarding them and breaking up that relationship. Anything that acts as sort of a measurement on either one of those particles will break up the entanglement. So maybe you want to check that it's still entangled without breaking the entanglement yourself. You couldn't measure both of these separately, because if you did, the act of measuring will destroy the state. But there is a particular measurement that you can do of both of them at the same time, which will tell you whether the state is still the one you hope it is, and therefore whether it's still entangled or not. One example of this type of measurement is called a Bell basis measurement. And to be honest, they're not that difficult, but even so, I've decided that I don't want to put it into this video because it will kind of needlessly complicate things. So instead, I'm going to link you to some good resources about Bell basis measurements. Alright, so the third and final rule, the measurement collapse rule, is actually fairly straightforward. If you have a multiple particle state like this one, and then you do some sort of measurement on it, let's say that you measure this electron in the up-down basis and this one in the horizontal-vertical, then what happens to the state afterwards? For example, after measuring down and horizontal, then what do you think the new state should be? Well, in this case, it's very similar to the measurement collapse rule for one particle. You look at the part of the state that represents this outcome, which is this one, and you leave that part and you delete everything else. So you're left with this. And I got rid of this coefficient as well because I need to renormalize this state so that this has length 1 and this has length 1. So this vector now has length 1, and this is our new post-measurement state. But let's say, for example, you have this state. This is actually a state that you could factorize quite a lot, but let's say that you're just being lazy, you have this unfactorized state, and you want to figure out what is the post-measurement state after you only measure this particle and I found it to be horizontal. Well, here there's two ways I can go about it. One is I just look at the parts of the state that are horizontal, so that's only this part of the state, and we delete everything else, and then we normalize, and so that result is just this. But when the particles aren't actually entangled like this, then I think that it's also quite easy to do it in factorized form. So let's first factorize this state. So this is the factorized form. By the way, you will get much, much better at very quickly being able to tell whether a state can be factorized and what it can be factorized into with some practice, of course. So if this is the state, we're now interested in just measuring this, and that doesn't affect this particle whatsoever. So we can say with certainty that this part is just going to stay as it is. But here, this only corresponds to this state. So this one gets erased, and we need this state to be normalized, so to have length 1. So get rid of this factor, and that's your result. All right, well done getting through all that. Let's just summarize quickly. So the first rule we learned was this superposition rule, which remember says that all states are vectors. But what do multiple particle states look like? Well, if they're not entangled, then they just look like write the state of the first particle, then write the state of the second particle, put them together. That's all. But in general, you can have states that are a little bit more complicated. So there's the state of the first particle and the second one, and then a different state of the first particle, different state of the second particle, etc. Next, we have the measurement probability rule, which says that the probability of outcome xp in this example would be just looking at this coefficient and taking the mod squared. However, if we're just interested in the probability of outcome x, then what we have to do is we have to first make sure we factorize this state so that we pull all of the x terms to the front, and then the bit for the second particle we must make sure to normalize to be length 1, and now the resulting coefficient, we take the mod squared of this. And finally, we have the measurement collapse rule that says that if you got the outcome x, so in this case, then you look at this state and you get rid of all those other terms that didn't involve x. You also get rid of this coefficient because you need to normalize, and the new state is this. If, on the other hand, you were measuring both x and p, then in that case, you would just get rid of all the other terms like that. You would just end up with xp. And so now you've actually met the completely general version of these three rules. So there actually isn't that much extra quantum mechanics that you need to learn. But of course, it takes a long time to really let these rules sink in. So if you're interested in doing extra problems, then there's a link in the description to a live version of this course. Thanks for watching.